Hi, in this podcast we're going to look at uncertainties and graphs. So how can we express uncertainties when we're graphing our data, and how can we actually use those graphs to process in part some of our uncertainties. And this is the last part of uncertainties and errors, and we will be relating it back to our continuing example of the pendulum. So we're going to be finishing off all of the data booklet sections that we haven't already examined. And as I said, we're going to be relating this back to the pendulum example that we've developed in previous podcasts. As with all of uncertainties, there's never any absolute one way of doing it. The IB has some recommendations, but those aren't always the only way you can do something, and you probably wouldn't be penalised if you were to adopt a different method, although you would have to justify that. Whereas with everything, the best practice is by doing, and you should ensure that you get plenty of practice in doing this before you have to implement it in a lab situation for your IA, for your extended essay, if you're doing one in physics, and also if there are any data analysis type questions in the exams that you are doing. Okay, so moving on. So to recap, we had a table 3, which evolved from table 2, which was created from table 1, which shows how the average period in seconds makes with the length of a pendulum, how it varies with the length of the pendulum. And we added at the end of the last podcast a 000, which we put the correct number of decimal places in to keep it consistent with the rest of the data. But that doesn't apply for every graph. Not every graph will have an origin or a data point at the origin. This one does. You're going to have to think about the situation and extrapolate from your data to see if that is justified in your case. So we have a length of pendulum with a built-in uncertainty. We have the average period in seconds and an uncertainty, an absolute uncertainty for that average period in seconds. And we can plot this on a graph. I am using here Logger Pro. You could use Microsoft Excel is another very good choice. Logger Pro is perhaps easier to use at time of making this video. The advantage of Excel is it's more universal. After you've been studying this subject, I sincerely hope you will go on to university and continue to do advanced research. But even in that case, you'll be more likely to be using, well, probably more specialist packages, but still more likely to be using Excel than Logger Pro. And if you don't go into physics and you go into another area of human endeavour, then Excel still may form an important function there, while Logger Pro will not. At time of writing, Google Sheets is developing, but still not got the full range of analytical tools that we need in physics. And I would say the same for Apple's numbers spreadsheet as well. Anyway, so onto the graph. So this is an XY scatter plot. It is almost inevitable that you will do an XY scatter plot. I can think of very, very few occasions, particularly when it comes to analysing data from experiments, where any other type of graph is acceptable in physics. So you choose, generally the independent variable will go on the x-axis and the dependent variable will go on the y-axis. Again, that's more of a guideline than an absolute rule. But if you do anything different, then you should be trying to justify that choice in a comment or in the caption of your graph. So there it is, plotted a little larger so we can see it properly. And the first thing you would generally try to do is form a line of best fit. Oh no, before that, sorry, adding some error bars. So here are some error bars in the data. Notice that the error bars in length plus minus 0.1 meters are consistent, whereas those error bars in the y-axis do vary slightly, as we saw from the table. Now is when you can try to add the linear fit. I'm not going to, by the way, do a video on, or not going to include in this podcast, any examples of actually using and how to use Logger Pro. I may do additional videos. The processes might change as software goes through revision, but I believe that the basic principles, which is what I'm illustrating here, will remain more consistent. Okay, now recall that 0, 0 is a point in this data graph, and you should rapidly see, even if you knew nothing about the physics of pendulums, that a straight line graph is not really appropriate here. It's a big clue if you try and draw a straight line graph and you end up with data that's sort of below the graph, heads above, stays above for a while, and then heads below. And that's consistent, or vice versa. And both of those will indicate that you're more likely to have a curved graph on your hands. Notice also that the line does not go through all of the error bars, but to be honest with you, that's likely to happen quite frequently anyway. Your error bars plot your expected levels of uncertainty. You might have additional unknowns that contribute to the overall lack of precision and or accuracy. So yeah, linear best fit, you can always try it, but be aware that it will not always fit. How to make one that fits? Well, you've got two options. One is to just try different options out and see if one fits. The other one, though, would be to look at the physics knowledge that you have or you can research and find what graph you would expect your results to be. One thing you should not do, by the way, is just try to fit automatically a high order polynomial. You'll get a line which goes through or near to all of the data points, but it's unlikely to be very meaningful in terms of the physics behind it. Because the physics behind it is what we can't forget in all this. And particularly at IB diploma level, it's unlikely that you're going to be working with a large amount of completely unknown physics or doing experiments that have not been done, at least in principle, before. In this case, pendula are part of the subject guide. They're an additional higher level part of the subject guide in the current version of the syllabus, but that should not prevent you from analysing data and maybe doing this as part of an IA, because you can take your subject content from wherever you like, including the additional higher level material. And the relevant equation here is t, the period of the pendulum, equals 2 pi the square root of L, the length of the pendulum, divided by g, where g is the local gravitational field strength here on Earth. What you're trying to do with your graph is basically linearize it. So you want a straight line graph. Because if you're going to get information out of a graph, then the most clearest information you can generally get is the gradient and the intercept. But both of those concepts are easiest to do and hold most meaning when you have a linear graph. So how do you turn things into a linear graph? Well, a linear graph has to form y equals mx plus c, and if you can assign something to y and something to x, then potentially you will get a linear graph. In our case, if we take the equation t equals 2 pi root L over g and we do the same thing to both sides, so we will get t squared equals 4 pi squared L over g, getting rid of the square root. And at that point, we can assign these to the y equals mx plus c relationship. So t squared goes to y and L goes to x, so those are our two variables, are our 2 points on a graph. 4 pi squared over g is assigned to the gradient, and note that that works and should give you a straight line because g is a number. It's not a variable, at least in this experiment. Yes, it will vary if you move through space, but within the confines of this one lab, it should be treated as a constant. And finally, there is no corresponding term for c, so we just assign c2 plus 0. So that's the equation that we would be expecting to determine our relationship. And indeed, if you plot length against t squared, you'll see that the data points are now more linear. Now for this exercise, I have only from this point plotted the error bars on the x-axis. That's just to make life a little bit simpler and shorter for this video. That's a decision that you would have to make though. Do I plot the x-axis or the y-axis, or try to do both? I would generally advise against doing both. I decide which is the more significant. And a average linear best fit does quite fit this data well, thus demonstrating that the equation is most likely an appropriate one for our experiment. We have the information that Logopro gives us, so it tells us it's a linear fit, it tells us the equation of a straight line in its own version, it tells us slope, and it tells us the y-intercept. Notice the y-intercept is relatively small. It's still there, this is real world data, but it's relatively small. The correlation and RMSE, root mean square, etc. Are there for to see how good a fit this is, but I'm not going to be explaining them in this podcast. And the important point is the M slope, 4.339 seconds squared per meter, which, as we have previously seen, is going to be related to numbers and the gravitational field strength. In fact, we can analyze in that context. So the gradient is 4 pi squared over g. We can rearrange that to give m equals, where m is the gradient, not mass or anything. The gradient here equals 4 pi squared divided by g. So therefore g equals 4 pi squared divided by the gradient, and therefore we can plug the numbers in there, and we get 4.339 using that for our gradient and 4 pi squared. We get a value for g of 9.1 approximately meters per second squared, which, if you've looked at this part of the physics course, you'll know is not too far from the correct answer, which should be around 9.8, 9.81. In order to give us an uncertainty in that gradient, it's relatively simple. We just draw two more straight lines. So LoggerPro enables to do that relatively simply. And by drawing these two straight lines, we get like a maximum and a minimum value for the gradient. So our result, 9.1 meters per second squared, came from analysing that 4.339, but the maximum and minimum gradient lines indicate that that value could actually somewhere between about 4 or 3.999 and 4.689 based on our fitting of the data. Plugging these into the equation, we get a minimum value for g of 8.419 and a maximum value of 9.872. We take those two measurements and we find the range, and we take the range and divide it by 2 as the similar method as we saw with our process data, to gives us a range divided by 2 of 0.73 to two significant figures, from which we can get that g, the value of g that we calculate, equals 9.11 or 9.10 based on this number here, plus minus 0.73 meters per second squared, which is aligned with what we expect. But you should also, in your analysis, just describe what you found. And so the equation that for your pendulum that you found was t squared equals 4.339L minus 0.052. It would be a good idea, again, to go and add some errors into these two things here. The error in the gradient you would get from finding the range divided by 2, as we have described here. And the error in the y-axis, I haven't gone through and done it on this graph, but you could extend these lines down here. Again, find the range between the maximum and minimum intercept and divide that by 2 to give you a similar thing. Okay, so hopefully that is all of uncertainties and errors accounted for. Apologies if this video was a little bit longer than I had hoped, but I hope it was useful.